Welcome back. So we're going to go into image classification. But before we start, hit the like button, subscribe, share this with anyone you know taking the AWS Machine Learning Associate exam. So image classification, understanding what, not where. So image classification represents computer vision's most fundamental task, answering the simple yet powerful question, what's in this image? Unlike object detection that localizes multiple items with bounding boxes, classification assigns categorical labels to entire images, identifying their contents without specifying spatial locations. So this distinction matters practically. Medical imaging systems need to know whether an X-ray shows pneumonia, not precisely where in the lung the condition appears. E-commerce platforms require product categorization for search and recommendations, not item coordinates within photos. Wildlife conservation efforts benefit from species identification and camera trap images without needing exact animal positions. So SageMaker provides two distinct image classification implementations, each built on different deep learning frameworks and offering unique capabilities for supervised learning tasks, where labeled training data enables models to recognize visual patterns. All right, so here are the frameworks. One, MXNet. All right, so SageMaker's dual implementation approach reflects different optimization priorities and provides strategic flexibility based on project requirements and team expertise. MXNet, right? This builds on Apache MXNet's optimized CNN implementations, and it offers a pretty straightforward training workflow with proven architecture. The implementation supports both full training from randomly initialized weights and transfer learning that leverages pre-trained ImageNet models like VGG and ResNet as starting points. MXNet version expects standard input formats like JPEG or PNG images organized by class labels with optional .lst index files or record.io format for optimized training throughput. This flexibility accommodates different data preparation while maintaining training efficiency. Then you have TensorFlow, all right? So this provides access to TensorFlow's extensive model garden and TensorFlow Hub, enabling modern architectures like MobileNet for edge deployment, Inception for balanced performance, EfficientNet for state-of-the-art accuracy, and various ResNet configurations. This architectural diversity enables optimization for specific constraints, computational efficiency for mobile apps, accuracy for cloud-based systems, or balanced approaches for general applications. The TensorFlow implementations, model-specific configurations provide fine-grained control over training behavior. Though this flexibility demands deeper understanding of TensorFlow's ecosystem and chosen architecture characteristics. Transfers. All right. So transfer learning. Both implementations support transfer learning, a critical capability that transforms image classification from data-hungry endeavor to practical technique. This requires moderate-sized data sets. So rather than learning visual features from scratch, transfer learning initializes models with weights pre-trained on ImageNet's millions of labeled images. These pre-trained models learn universal visual representations, edge detectors, texture recognizers, shape identifiers that transfer effectively to new classification tasks. A model pre-trained on ImageNet's diverse categories provides robust feature extractors that require only fine-tuning. So the final classification layer will be good for domain-specific categories. This approach reduces required training data. Where training from scratch might demand tens of thousands of images per category, transfer learning often achieves strong performance with hundreds of examples per class, accelerating project timelines and reducing annotation costs. All right, so for data prep, let's see. All right, so data prep and organization is crucial, right? Image classification's supervised approach demands properly labeled training data where images belong to specific categories that models learn to recognize. The simplest organization strategy would use directory structures where folder names would indicate class labels, right? So you'd have one for, if you're doing animals, you'd have one for cats, for dogs, for birds, right? And then that would be for your training. And you'd have a validation one for cats and dogs and birds, right? So the structure would enable both human understanding and automated processing, with SageMaker inferring class labels from directory names during training. For MXNet with large data sets, consider .lst files or record.io format that provides optimized input-output performance, right? These formats reduce storage overhead through compression and enable efficient streaming during training, particularly valuable for datasets with thousands of images per category. Standard image formats like JPEGs for photographs or PNG for graphics require lossless compression. So this will work across both implementations. and to ensure consistent image quality and resolution appropriate for your architecture with 224 by 224 pixels will be the standard input size for many pre-trained models. And let's go a little hands-on, all right? So you're gonna go to SageMaker. Remember, you can load all your stuff in S3, okay? We'll go to training, training jobs, create training job. All right, job name, let's see, image class test. Okay, choose appropriate IAM role, what you need for S3 access. S3 access, CloudWatch access, SageMaker access. Okay, your instance size, your algorithm, obviously. So you're choosing the built-in, so your image classification, and we don't have TensorFlow, that's fine. Okay, so you choose the image classification here, then you select your instance size. Okay, so right here. Okay, so image classification, CNN really demands GPUs for practical trainings. So you could select one like ML.P. Okay, so one of these, the MLP3 should be suitable. And then for small scale, well, this would MLP5 4x would be good for a large scale one. This would be good for a small scale one. Okay. And then you want to make sure that you're doing cost effectiveness. Let me see, P2. We go P2. We go P3. So it's just P3. Okay, so they upgraded it. All right. So for massive data sets, consider multiple GPUs. All right. So you could do the MLP3, let's say 8x large. All right. Multiple GPUs on a single machine. And then you want to set aside about 100 gigabytes for data sets with thousands of images, right? And keep alive periods. Oops. Let's say 360 minutes. Oh, no, 60 minutes maximum. I keep forgetting that. Encryption for your data. Maximum runtime, 24 hours. VPC, set that for network isolation. That'll include subnets and security groups. And then you'll do your hyperparameters. So let's see some interesting ones that we want to do. Number classes. All right, you do this one to match the distinct number of categories in your data set. So you got 1,000 images, put 1,000, right? Let's see, number of layers. All right, so this is for architectures for variable depth. So you choose between shallow for simpler tasks and deeper for more complex categorization. All right, so we're doing 56 seems good. Let's see. See if we have some image stuff. Okay, image shape. All right, so this will talk about the dimensions if it differs from the default 224 by 224. All right, so larger images will need finer detail recognition, but it'll increase the memory requirements. Okay, and then let's see. Batch size. Yeah, so since we're doing MXNet, all right, so this will be between 32 and 128, right? So this is balancing training stability with memory constraints. So let's put it at 64. Okay, the epochs, okay? This is the training duration. So usually between 20 and 100 epochs, right? So let's set it at 50. Depends on the data set size and transfer learning, all right? And then for transfer learning, enable pre-trained model initialization through the algorithm. All right. And then from here, you'd set your train name, your input mode pipe is through S3, file is downloaded locally, and it goes through. So it's better for development. Compression type, application size. The format, next application, images, compression type, we don't need that. Wrapper, we don't need that. Select your source S3 bucket, your checkpoints to save, which works well with the enable manage spot training. So you can, have any shutdown with spots which save costs, you should be good to go. And then you set that checkpoint S3 right here. Then you set your output for your final. Create your tags, key value pairs, and click create the training job. All right. So from there, you check on the SageMaker dashboard or CloudWatch logs, and then you'll see the updates on loss values, accuracy metrics, and processing throughput, right? So the training duration will basically vary depending on dataset size, models, architecture, transfer learning, instance size, all that. So we'll hit cancel. And when it's complete, your artifacts will be saved to that S3, and then you can use that to go forward with your training. All right. All right, so how can this be used? So image classification enables diverse applications across industries requiring automated visual understanding. So e-commerce platforms can use classification for product categorization, automatically assigning items to browsable categories based on visual characteristics rather than manual tagging. Medical imaging applications could employ classification for disease detection, identifying conditions like pneumonia, diabetic retinopathy, in retinal scans or skin cancer and dermatological images, right? So these systems would augment rather than replace medical professionals. And they could flag potential cases for expert review. And then manufacturing quality could use this for defect detection, automatically identifying faulty products on assembly lines based on visual appearance, right? So this automation would enable 100% inspection coverage with manual review, right? And in wildlife conservation, like we spoke of earlier, could use classification for species identification in camera images, right? So this will enable population monitoring and behavioral studies across vast geographic areas without constant human observation. And cost, right? So like most of these, the GPU requirements are going to be a cost consideration. So you're going to have to be strategic with this. So training costs will scale with dataset size, model complexity, accuracy requirements, and instance types. So a GPU could scale from $1 to $6 an hour, depending on your instance type, right? So use those spot instances with the checkpoints in order to have recovery and then not lose progress with interruptions. And then you basically have to justify what your costs are going to be over time. And at that point, you can consider something like batch transformation for periodic classification tasks rather than like a persistent endpoint. At the end of the day, SageMaker's image classifications makes computer vision a lot more manageable by providing an implementation of a proven architecture. And so you could use it to categorize products, detect medical issues, identify whatever, and make production grade classification systems. And you wouldn't have to use a managed CNN architecture or use it or create one from scratch. Regardless, thank you for joining. I appreciate your time. Remember to hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Have a great afternoon or evening or morning. Bye.